Job number 11 is entitled 40-watt power amplifier. In our DJ mixer project, we built a power amplifier with low distortion by using a feedback loop. We use the same principle here. However, if our op amp can only supply plus or minus 25 milliamps of output current, and our output transistors have a beta DC or beta F around 25, then the maximum current that we could get out would be the maximum current of 25 milliamps times the beta F of 25, which would be 625 milliamps. If that flows into an 8 ohm load, we're looking at about 5 volts. So what's our power out? Well, it's going to be the RMS value squared divided by the impedance of the speaker. We'll just say it's 8 ohms. So 5 volts divided by the square root of 2 would be the RMS value. Squaring that and dividing by 8 would be 1.56 watts. So clearly that's not going to work for us to make a 40-watt amplifier. We're going to need a current booster to make this work. This is our power amplifier with a current booster, and was actually published in a Popular Electronics article many years ago. Let's even roughly figure out how it works. So here's my amplifier. I've got hooked up to it a simple power amplifier that we were using before. And then we're going to hook this up to another amplifier, which will give us a current that can drive the load. Now when the voltage is positive here, we forward bias this junction, which means we reverse bias this junction. So this is cut off. If this is cut off, then this is cut off. So the bottom half is off when the top half is on. Now if there's current flowing in here, you can pull it through here. Okay, so that's going to turn this transistor on too. So the gain between here and here is roughly that of emitter follower, just one. And then the gain from here to here, I've got basically a kind of a common emitter amplifier structure. Because if you set this equal to 0, we're going to be grounding the emitter. So we're going to get some voltage gain from the op amp, quite large, and a gain of 1, multiply that by 1, and then multiply that gain whatever the common emitter amplifier is going to give us. Now the same is true for the bottom half. When this goes negative, this gets forward biased, this gets cut off, this gets cut off, and then this becomes another common emitter amplifier. Now we're actually going to introduce some resistors here, R3 and R4, to actually lower the gain of this stage because we don't really need it. The voltage gain here is pretty high at low frequencies. It's on the order of about 200,000. But if you have an amplifier and give it some more voltage gain, then you can think of this as some super op amp. And so we put feedback around it. Then the voltage here is just simply the input voltage times 1 plus the resistor ratio. Now if we want to deliver 40 watts, let's figure out what the voltage needs to be out here. The 40 watts would be the output voltage squared RMS divided by 8 ohms. So we can solve this equation, cross multiply, and then take the square root. That's 17.89 volts. And then the peak value would be multiplying that by the square root of 2. So to deliver 40 watts out, we need to have the output to swing to a maximum value of 25.29. This statement would be true if it were swinging negative. Now the problem with this is that we're using an op amp, and it typically can't have a power supply bigger than 20 volts. So let's run that LF411 with a 15 volt power supply, and then let's power our current boosting amplifier with a 30 volt power supply to get enough voltage that we can get this much out. Now in lab you'll need 2 of the 200 watt power supplies we have, which are HP 6002. And these will just be our regular power supplies we've been using in the course. Let's see if we can figure out how much current gain we're going to have. Let's take a look at again having the top half of the circuit on and the bottom half off. So again, when Q1 is on, Q3's emitter base can turn on, and Q3 can supply some of the current needed by the load. I'll do some calculations here. Let me go back to the previous page and just write the answers on there, and you can look at this while I'm doing that. The current that's in the base of this transistor, so this would be I sub B3, is roughly equal to the current that's here. Because the current in this resistor is going to be, roughly the voltage across here, which is around 0.7 volts divided by 10K, and this is about 70 microamps. That's pretty small. So you kind of neglect that current. So this is roughly I sub B3. Of course, that's the collector current of Q1. The current coming out of here is going to be 25 milliamps maximum, and that's going to be the base current of transistor 1. All right, let's go figure out the output current back over here. So the current in here is going to be equal to beta F, or beta DC, times IB3. But IB3 is equal to I sub C1. Okay, then what's I sub C1? That's going to be equal to beta F times I sub B1. So that's going to be beta F times I sub C1, which is going to be beta F times I sub B1. And this current roughly all goes into the load because the current down in here is small. We can pick the resistors large, so it's a ratio, it still gives us the number we want. The current in the load is going to be the beta F squared times IB1. But what's IB1? That's at most 25 milliamps. So let's go back to the page number 3. And those calculations are shown here. So that means that the maximum collector current in transistor 3, which is roughly going to be the current going out, is going to be the beta squared times the current coming out of the op amp, which could be as much as 25 milliamps. So that would give us 15 amps. Now if we went 40 watts out, we got an 8 ohm load, and then the biggest voltage we can have across the load is 25.29, then we're looking at about 3.2 amps or so. And so we got more than enough current gain to be able to supply that current for our load. Now I made this whole argument with the top half of the circuit being on and the bottom being off, but you can do the opposite and do the same kind of calculations with the bottom half. As I mentioned before, without the resistors R3 and R4, there's a fairly high voltage gain in that second pair of transistors, Q3 and Q4. And of course, you don't really need that because you have a lot of gain with the op amp. So these resistors R3 and R4 are kind of put in there kind of like a non-inverting amplifier to bring down the gain and also to lower some of the distortion. Our first design task is to figure out what are the values of R3 and R4. Well, let's take a look at our circuit, maybe at one instant in time, and see if we can make some decisions based on that. Most voltage I can get out of here with a 15 volt power supply is a little bit less than 15, say plus or minus 13. So let's assume that the output is swinging positive at node 5. Here's V5. And let's let this be its maximum value, say 13 volts. For positive here, then we forward bias this junction. This voltage here would be equal to 13 volts minus 0.7 or 12.3. Now I want my output to be 25.29 volts when this occurs. In other words, here's my V out. It's going to also be a sine wave. And then we have a value here of 25.29 when this was 13 volts. So that's my desired output. Now can I use that to figure out what R3 and R4 have to be equal to? Now let's do a step 4 down over here. Now when this is 29.29 volts, we said that the current here was about 3.2 amps. There's very little current going down here, so that's basically the current that's going to be flowing in the collector. I have to allow some current to come back in here, but not a lot, so that most of this can go into the load. So let's just pick a value here. I don't know, say maybe 100 milliamps or so of the 3.2 amps that's here, and let it go back into here. So now if we know the voltage here is 25.29 at one instant of time, and this is 12.3, if we let 100 milliamps go through here, that would make this a 130 ohm resistor. So under this one condition, we could figure out what R4 would have to be equal to. What about R3? Well, the voltage here is 12.3. The current coming in here is 100 milliamps. And now what's roughly the current coming into here? Well, this is cut off when this is forward biased, so that's off. This current that's coming out of the base is going to go into the collector. And basically, what's going to come out of here is roughly beta F plus 1 divided by beta F times bigger, or just roughly equal to the same value. It's 3.3 divided by 25 milliamps, if beta F is 25, is going to be coming here, add to this, and give me the current in here. So I can then figure out the value of R3. It's going to be 12.3 volts, 100 milliamps plus the 3.3 over 25. It's about 53 ohms. Now this whole calculation was based on beta F being 25. In other words, beta DC being 25. It turns out it's not equal to that, and I'll talk some more about that a little bit later in this lecture. We did a derivation on the previous page with V sub x being plus 13 volts and V out being plus 25.29 in 1 instant of time. And this is with the top half of the circuit on. The same would be true if we had V sub x equal to minus 13 volts and V out being minus 25.29, the bottom half being on, the top half being off. Get exactly the same results. Now we need to pick the resistors R1 and R2 to have a stable circuit. So let's think about how we might be able to do that. Well, our current booster has some kind of a voltage gain, has some kind of a phase response with frequency. So again, you kind of think of that as a new op amp, maybe a super op amp, that can give us a lot of voltage gain and a lot of current gain. So it has some magnitude and angle versus frequency, just like we did for any op amp. Now we developed a beta theory for looking at stability in circuits in chapter 4, but if you noticed in all these things that we did, our derivations, we didn't have a load hooked up. And so we'd have to modify our theory to be able to do that. Well, a much simpler way to do this is simply to take that load, which is the speaker, and bring it inside the op amp. Now there's nothing hooked up out here, and so our theory is still the same. So we have to see what's going to happen now if we were to bring the speaker inside of our LF411 and our current booster. But again, this is going to have some overall voltage out over voltage in. On the simulation on the next pages, I'm going to call this node 1, 0, 5, and 11. So basically I'm going to ground this point and then sketch the magnitude and angle versus frequency. But again, there's two things that are going on here. The top half is on and the bottom is off, and then vice versa. Now when we test the op amps open loop, we have to worry about DC offsets. Now our macro model has, for the LF411, has virtually no input offset. But we have a power booster hooked up, which has PNP and NPN transistors, so we could get some offset in there, which would cause the output to saturate. Say put in 0 volts DC on our initial test and see whether the top half or the bottom half is on. So I asked for the operating point, and I just listed the first 5 output voltages here. There are some more, all the way up through 11. And the value at node voltage 5, this is the output of the LF411, is a minus 1.3187 volts. That means that the top half of the circuit is off and the bottom is on, and we'll check that just shortly. But this didn't hit the plus or minus 15 volt power supply, so we didn't saturate those output transistors. Let's see what happens with our individual listing of the transistor parameters because of the operating point. Q1 and Q3 are the top transistors, and you can look at their collector currents. They're very, very small, which means that they would be in cutoff. If you look at the collector currents of Q2 and Q4, it's the bottom transistors, you can see we have milliamps and really hundreds of milliamps in the transistors. Now, this is a PNP, and so our definition of the collector current is the opposite of what's in SPICE, if you recall from 302. Now when I did my calculations for the resistors R3 and R4, I was saying beta is around 25. And that's the case when the current in the collector goes up, the beta DC goes down. Now here in this testing, the base current is quite small. It's in microamps and just a few milliamps. You can see it calculates the beta DC at 85.4 and 126. But that number will drop as the current goes up. And I'll talk some more about that a little bit later in this lecture. What we're seeing is our input has forced the bottom half of the transistors to be on and the top to be off. Now we take a look at the frequency response of that resulting circuit on the next page. So here's a plot of node voltage 11, but node voltage 1 is equal to 1 volt, so this is the transfer function. So here's my open loop curve versus frequency, and then here's the phase angle versus frequency. And you can see here that eventually there's one pole, and then there's many more poles kicking in because of all those transistors in the current booster. When we cross 0 dB, the phase angle is equal to minus 230 degrees. So we had a gain of 1. The circuit would not be stable. The overall gain here is 121 dB at low frequencies, and the LF411 by itself is 106 dB, or a gain of 200,000. So we've got about 15 dB or so, and that's about a gain of 5 or 6 from that current booster stage. We're lowering the voltage gain, but we do have quite a bit of current gain. All this was done with the top half off and the bottom half on. Do we get the same phase margin and phase response from the top half of the circuit? Well, let's force the top half on and see what happens. Okay, suppose that I want to make the node voltage 5, say, a plus 1.5 volts. Well, the gain of that LF411 at DC is 200,000. So if I put 7.5 microvolts on the input, it sees a gain of 200,000, it'll make the node voltage 5 equal to about 1.5 volts. Let's do that. And now we're biasing the top half of that power amplifier and shutting off the bottom half. What's shown here is that node voltage table we get with the operating point. And here's our node voltage 5. We were shooting for about 1.5 volts. It's 1.6, but it is smaller than the 15 volts of the power supply, so we definitely haven't saturated that transistor. It's still in the active region. Didn't show node voltage 11 here, but it's around 3.4 volts. Check the transistors again. Now take a look at Q1 and Q3. You see that the collector currents are in the milliamp range and in hundreds of milliamps, and that Q2 and Q4 are very, very small. So they're cut off, and Q1 and Q3 are active. So now we can get a Bode plot of our open loop gain and the angle versus frequency. So here's our open loop gain, similar in shape, but the low frequency value of gain is different. It's 120.4. And when we cross a gain of 1, it's around 3.16 megahertz versus 2.7. And the phase angle here is a minus 245.1. This is actually worse for stability than the previous case. So we have two things going on here, when the top half is on and when the bottom half is on. So as you're designing the values of the resistors for R1 and R2, you have to take this into account and make sure it's stable under all conditions. So using our beta network theory, given that we've got the open loop curve magnitude and angle, and we've got resistive feedback, could you pick the resistors R1 and R2 to get a phase margin of 60 degrees? Okay, I'd like you to then run your closed loop simulation and verify that your selection of R1 and R2 are stable. One way to do that is to do a transient analysis with a sine wave input, say of 10 kilohertz, and select the value of the magnitude of the input such the output doesn't clip. The circuit's stable, increase the input amplitude until the output clips. Now, are you able to get plus and minus 25.29 volts without clipping? If not, you have to go back and repick resistors R3 and R4. I'll give you a hint. You won't be able to get this much out, and so you have to go back and pick R3 and R4. The problem is that I assumed beta F, or beta DC, was equal to 25 when I picked R3 and R4. It turns out it isn't. So what I need to have you do is take this simulation that you have and measure the value of the base and the collector currents of Q3 and Q4 when they have maximum and minimums. And then calculate the actual value of beta DC at one instant in time. And you'll see that as time varies, the value of beta DC, or beta F, is going to be changing, and the smallest value is actually when the currents in the base and the collector are their maximum value. Next thing to look at is what are the power ratings of the resistors R3 and R4. So I'd like you to estimate what's the power dissipated in each resistor. We have very small holes in the proto board, and so we're going to have to use our quarter watt resistors and use them in parallel to create a bigger wattage resistor. Large power resistors won't fit in the holes that we have in the proto board. Okay, I'd like you to do the above with your lab partner and make 2 copies of your pre-lab. Turn one into your lab instructor and keep one for yourself. And this is the background for Lab 11.